Hi, I'm Andrew Mason from RAR UK Automation. Today I'm here to discuss 2D and 3D vision sensors in particular and where they fit well with collaborative robots. We will also discuss how easy they are to use, the benefits of use and how they fit in with other sensors for applications. First, I would like to talk about senses and where human senses that are often taken for granted are required by robots to take on the application that humans do without thinking. Most of us have 5 senses, although some people claim to have 6. 2 of these are commonly required by robots to carry out pick and place and or assembly tasks. If we think of a human completing a task, then we'll often use our vision sensors or eyes to recognise the correct components, and then we'll orientate them into the correct position. If an assembly task, again, we need to select the components, orientate them and fit them together. Here is where the sense of touch becomes important. We usually need some dexterity to place components gently into position, or if fixing 2 together so that they feel and they are clicked into position correctly. For a robot to do this, we need a force sensor to know when the part has been placed upon a surface or perhaps clicked into position. This is where a combination of vision and force is a powerful tool for robots to carry out human tasks. So 2D vision cameras can be either mounted remotely or more often for cobot applications they are mounted on the robot tool flange, or in the application shown here, actually directly on the wrist for ease of use and also to avoid conflict with the robot gripper or other tooling. For cobot applications, the cameras also come with easy plug and play software, and so in keeping with the philosophy of cobots to provide a system suitable for use by end users to develop their own applications and operate with any expertise level. This is typically supported by documentation, how to do videos, and with the systems that we offer, site visits by our application support team to provide the customer with a helping hand. In this video, we see a slimline camera mounted at the robot wrist to be as inobtrusive as possible and avoid interference with the robot gripper. The lighting, exposure and focus has automatic and manual adjustment options to enable the camera to find the multiple components and set the pick location. Now we see barcode reading component verification for QA in process control requirements. Here we see colour verification in action to, in this case, differentiate identical geometrical components of different colours for correct selection or sorting purposes. This is a very typical machine loading example where we don't actually need the camera to find the individual billets as positions are located in a tray. However, the camera reads the data matrix code to data tray orientation with a visual offset. This technique can also be employed with a data matrix code on the machine tool. This allows fast setup if relocating a robot between different machines. So now coming on to techniques and how do they work. The Easy Teach software has default settings to allow the Easy Teach setup. These can be adjusted to enhance the benefits of the onboard light source for a particular light environment for the snapshot position. Once the image has been taught or a snapshot taken, or the image generated from a CAD model, this effectively becomes the master that the camera in the application needs to find. Here we set how closely the new image needs to match the master. This is set as a percentage term against the pattern match. This needs some careful consideration, as a high percentage can result in not finding a component that may have a small difference, whereas a very low percentage can result in incorrect components being picked. Invariably, the operator will recognise where this needs to be set to gain the best results and find the best compromise. Okay, so come on to talk about specifications and features. Typically, the EasyTeach software tool allows for fast deployment and flexibility for fast changeover between or to teach new applications. The components can be taught in a number of ways. If a geometrical shape, then the dimensions can be input into a template to set the product image. If not geometric, then the camera needs to take a snapshot to teach the master image. Alternatively, many systems can create a vision model based upon a CAD file of any part. Other features and capabilities include colour verification, barcode and 2D code reading, and also multiple images can be detected in a single snapshot, and this saves on cycle time, so the camera doesn't have to keep taking multiple images. Machine tending is a common application. Here, the randomly placed billets can be found with vision. This application is also using data capture to measure the robot and application performance. This assembly application shows a range of pick and place operations combined with dosing of a sealant and joining process before passing the sub-assembly for further processing. This final video shows individual pick and place of components to a tray handling device. So now on to 3D vision. 3D vision systems naturally offer enhanced capability over 2D cameras to enable the additional dimension to identify components that are not or unable to be consistently presented on a regular plane. This gives the ability to find parts that might, for example, be fed via a conveyor, that are overlapping or sitting on top of each other, so they can be picked and placed randomly orientated parts from a box or bin, known as bin picking. These are then fed to the next stage of production, assembly or packing process. As with 2D vision camera systems, the camera and light source can be either remotely mounted or attached to a robot arm. 3D vision systems can operate in poor light condition and also with infrared cameras at low level lighting. As with 2D systems, the trend is towards easy to use software tools for plug and play solutions by the end user for flexible deployment of applications. The cameras again work on a pattern match compared to a taught or CAD generated image, with a percentage pattern match set to find the correct component feature. Typically, the software is managed on an industrial PC and camera resolutions are higher than those on simple 2D cameras. Naturally, this is reflected in the cost of the system, and it's always selection of a 3D system over a 2D solution will always need to be justified by the needs and benefits required in the application. A range of camera systems are available to meet the needs and range of fields of view, and where smaller or more detailed applications are required, high definition cameras are better suited. This slide shows the range of depths of field for bin picking with 3D vision, either using a fixed mounted camera or, if mounted on the robot, then can be set by adjusting the robot position relative to the work plane. Gripper selection can often be critical to a successful application, particularly with bin picking. Ideally, it is best to avoid the need for the robot wrist to go into the bin or stillage, and consequently, either vacuum or magnetic grippers on an extended stick is advantageous. This leads to a less accurate pick than would usually be achieved with a 2 or 3 finger gripper. To overcome this and get the benefits of both gripper types, the technique often adopted is to use a stick gripper to take the components from the bin and place this into a simple gravity fixture to locate the product more precisely, and then re-pick with a precision finger gripper such as this to place in an assembly. The slight disadvantage here is a resultant increase in cycle time. A technique to assist cycle time is the ability for multiple components to be identified as suitable for picking during one snapshot of the bin components. Here the software will identify the best matched component and pick this, then go back to the next best match and so on. A new snapshot is only taken when all previous suitable identified parts have been picked. Typical applications for 3D vision include picking goods from conveyors, bin picking from stillages of overlapping parts, raw materials, billets, and forging industry applications. Here we see 3D vision in an end-of-line palletizing application. 3D vision can be used to find a variable position component, in this case for a polishing application. In this video, we see a typical forging industry application, picking bulk raw material from a stillage. (2D and 3D vision is becoming increasingly popular for both cobots and industrial robot applications to enable freeing up of labour and reducing production bottlenecks and extending manufacturing production cycles within unmanned operation. Determining which tasks are most suitable can often be determined by the language we use to describe the task and how we emphasise the word, either in a positive or negative context. Consistent and repeatable is viewed as a positive for a robot, whereas mundane and repetitive is regarded as a negative if a task needs to be done by a human, which in turn can lead to mistakes and the human become bored. Robots with the help of human-like senses can do boring tasks 24/7, consistently without a break, with the benefits of robots not getting bored. As with all automation applications, careful consideration of the requirements needs to be conducted to create a specification. Fortunately, for the end users, help is available from industry experts through UKIVA, BARA, PPMA and automation providers. Thank you for listening. If you would like more information or have questions, I can be contacted through UKIVA and BARA.